Okay, so hello everyone. We are here for the 11 week 11 live interaction session. So let me just share my screen. So I hope my screen is visible and I'm audible too. So here, uh, this is week 11 live interaction session, and it's I think 9. So we have seen solutions till assignment 9, sorry, assignment 8. Today we are going to discuss the assignment 9. So, assignment 9 discussion. So before that, uh, I will quickly revise what is being covered in week 9, and then we can proceed with the solutions, because this assignment I particularly find to be very easy, and it won't take much time to complete it. So it's better that we devote more time to the theory part, so that you can revise everything. So uh, first of all, one should be aware of what is a module. So let R uh, be a ring, and I'm assuming that is a ring with unity. Okay, so uh, unity means just multiplicative identity. Okay, so this means uh, multiplicative identity. So then you can define an R module. An R module, here we are defining a left R module. So I'm writing left in the bracket. So it's an abelian group first of all. It's an abelian group, say M plus, M with the group operation to be plus, and then together it has some multiplication map from the ring R, together with the map R cross M to M, such that it maps the tuple Rm, R comma M to just R dot M. So from here you get that for all R belongs to R and M belongs to M, uh, this implies Rm should be inside M. Okay, so we need this to define the multiplication map from the rings. Okay, and then you also require that this map should be satisfying certain properties. So this should be satisfying first of all the multiplication with the unit of R, right? 1 dot M should be M. So here 1 is the unity of R. That is the multiplicative identity. So after multiplying an element M with a unity of R, one should get back the element itself. Okay. Second is should be the scalar multiplication should be associative in nature. That is alpha beta uh, multiplied with m should be equal to alpha multiplied with beta multiplied m. Okay, so this is, you can say, associativity of the least scalar multiplication. So this map is called scalar multiplication. Scalar multiplication. Okay, yeah, should write multiplication below. It should be called scalar multiplication. Okay. Now, this is one thing. Now, this map should be compatible with the addition operation also. And what I mean by compatibility is, third property says alpha plus beta, and this addition is in ring. Alpha plus beta should be equal to alpha dot m plus beta dot m. So this operation is, this is inside, this is happening in m, and this addition is happening in r. Okay, so addition of scalars of multiplied with the element of m is should be distributive in nature, and second kind of distributivity we can have is with the addition operation of the module itself. This is in m, and that should be alpha dot m1 plus alpha dot m. And whatever these things are, this should happen for all alpha beta belongs to R, and for all m, m1 and m2 belongs to m. These four properties should be for all scalars and should be for all elements of the abelian group m. So this is, you can say, a generalization of vector spaces. Vector spaces is over a field, but these here we have a ring, and over ring we defined a scalar multiplication for the abelian group, and that scalar multiplication satisfies these compatibility conditions, and uh, this is said to be a module. And why this left is coming? So maybe I would highlight this left. So why this left is coming? Because here, due to this multiplication is from the left. This r is being multiplied on the left. Okay. If it would be defined as m dot r, then we would have said it a right module. Okay. And similarly, these properties would have changed. Here it would be m uh, dot alpha beta would be m alpha dot beta, and something like that. All these scalars would have moved to the right, and similarly we would have defined the properties. Okay. So the left is coming here. So now one observation is, uh, abelian groups are modules over Z. That is for, I should write, all abelian groups are modules over Z. So over Z, the module structure is there for all abelian groups. In particularly for for an arbitrary ring, this module structure would not be there for an abelian group, but for over Z, every abelian group has a module structure, and that is let me tell you why. So let m plus be an abelian group then you can define the map. Then one can define a map from Z cross M in the way. So n is an integer, comma m. This is mapping to n dot m, which is equal to, so how n dot m you can define. So this is equal to 0 if n is equal to 0. Okay, so 0 times m you will say 0, and m as an additive operation, right? So you can write m plus dot 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 m. This is n many times, n times. If your n is greater than 0, and what if n is less than 0? You just take the negative of it. Negative of m plus m dot 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 m. Again, you have to take it n many times. So this you have negative. So this in this manner you can define a multiplicative map from Z cross Z to M. Okay. With every abelian group has a Z module structure, and of course, if every Z module has an abelian group structure, because every module over any ring is a abelian group. So you can say that abelian groups are in one correspondence with uh, Z modules. Okay, because every module is an abelian group, and every abelian group can be given a Z module structure. So okay, uh, that's it. And next we can define the homomorphism of modules. So next is homomorphism of modules. Okay. Yeah. So how one can define that? So you have two modules, like M and R are R modules. R is a ring over which the module structure is given. Then phi from M to N, such that phi of, then a map phi from M to N such that phi of M1 plus M2 is phi of M1 plus phi of M2. So you have, it respects the operation. So here this operation is in M, and this operation is in N, because phi's are elements of N. So uh, have this thing in mind. So yeah, and also it should satisfy the, it should be compatible with the module with the multiplication, scalar multiplication thing. So here this dot is in M, and this is in n again. Okay, because both of them has R module structure, so it makes sense what is R dot phi m and what is R dot m, right? This is a module structure in M, and this is from the module structure in N. So this any map that is compatible with the additive one and the scalar multiplication from the ring is called a homomorphism or R linear map. Okay. Now this is then the next thing is what is known to be a bilinear map. So a map F from M cross N to P is said to be Z bilinear if first thing is F of M1 plus M2 comma N same as F of M1 comma N plus F of M2 comma N. So it's compatible with the first uh, addition in the first uh, this thing, and first coordinate, and second property is it's compatible with the addition in the second coordinate. Okay. Again, it should happen for all M, M1, M2 in M, and for all N, N1, and 2 in. Okay. So yeah. So now one can define what is a tensor product of modules. This is the definition of Z bilinear. Something strange happened. How it suddenly happened. Let it be. Okay. So yeah. So I was just saying that now we have defined, as we have defined the Z bilinear map, we are in position to define what is called a tensor product, because that is the main aim of this week, to make you aware of this definition. So a tensor product of of two R modules. Here, let me just say Z modules. Yes, in the first lecture, it was defined for Z modules. Uh, tensor product of two Z modules, M and N, is a pair T comma alpha, where T is a Z module in itself, and alpha is a map from M cross M to T, which is Z bilinear. Z bilinear map with the following universal property. The following. So this thing you should be looking at very cautiously with full focus, because this is what we will be using again and again in solving the problems, the universal property. So the tensor product has the universal property that given any pair capital P and F, where P is a Z module and F is from M cross N, P is a map, is a Z bilinear map, then there exists a unique Z linear map F delta from T to P, satisfying F compose alpha is equal to F. So what is the situation? So you have M cross N, given a module M and N. So you have tensor product. Tensor product is a pair T alpha, where T is a Z module and alpha is a map from M cross N to T. So you are given this T and this map alpha. Then for any given pair PF, where P is a Z module and F is a map from this M cross N to P, there exists a unique Z linear map. So every this F induces a unique Z linear map from T to P. This has been induced such that this F is F compose alpha. So you go from here to here or from here, the diagram will give you the same thing. So this diagram is commutative. Okay, so that's what. So it means now an observation is tensor product is unique if it exists. So if tensor product of two modules exists, then it's always unique. Okay. So, so if in the question it's given that prove that the tensor product of these two modules is the third one, then what you need to do? You need to define a map such that it induces a map, and then you have to show that that induced map is actually an isomorphism. We will see this. Uh, First of all, let me define what is a free Z modules. So let S be a set, then a free abelian group. So every Z module is a 1-1 correspondence with an abelian group. So free Z module is nothing but a free abelian group. That's why I'm writing it like that. Is so free abelian group on a set S is a pair F comma gamma, where F is a Z module and gamma is a map from S to F, a set theoretic map such that for any given pair N comma F, where N is a Z module and F from S to N is a set map, there exists unique F delta from F to N such that F delta is Z bilinear, Z linear, and F compose alpha is equal to F. So here also the free group satisfies a universal property in the sense that free module satisfy the universal property. So you have S, any set from S to F, you have a map gamma such that for any given uh, pair N and the set theoretic map from S to N, that is F, there exists a unique induced map F delta such that the diagram commutes, that means F composed alpha is okay. That is free module. Now we said that tensor product we defined, and then we said that if it exists, then it must be unique. Now we will show that tensor product of any two modules actually exists. And uh, okay, so before that, let me just give the existence of this free module over S. So existence is, so you can take F to be a set of all maps from S to Z such that HS is equal to 0 for all uh, or but finitely many S belongs to S. So what does it mean for all but finitely many S belongs to S? It means uh, HS is non-zero for finitely many S. Okay, so it means HS equal to 0 for all but finitely many S belongs to S. So except finitely many elements of S, these maps are 0 everywhere. So you can also take it as a collection of strings of S, because finite strings say over the set say S equal to AB, A comma S is A comma B. So finite free abelian group generated by S is nothing but the collection of elements AI, BJ, right? Where I and J are varying over Z. And these indices are actually there corresponds to this map. So any element say A to B will correspond to the map H from uh, S, that is AB, to Z, such that A is mapped to what is the power 2 and B is mapped to 1. So except so here we have taken S to be finite. So if any map is definitely going to be uh, non-zero at finitely many places. But if you take S to be an infinite set, then also you can define it like that. And then you just collect the finite strings A, B, C, D and its powers. Whatever its powers, you can just say they are the images of those elements under this map, under the map from S to Z. So each element corresponds to a map and vice versa. That's why they have defined it like that. But we can also define it like that, that to collect that all finite strings. Okay. So if S is already finite, then you have always have finiteness. If S is not finite, then also you collect the finite strings, and that collection will give you the free module over S. Okay, or the free abelian group over S. I hope it's clear. Okay. Now, yeah, one interesting thing is, so we didn't give the module group action here. Sorry, the group of what to say, the group operation. So here the group operation is H1 plus H2S. Just add them in the usual sense. Okay, this is the operation, and the map. So F must be coming with the map, right? We said that something to be free module if it's a pair F comma gamma. Gamma is a map from S to F. So what is the map from S to F? That is again the most uh, natural map. That is any element S you map to map ES such that ES of X is equal to 1 if X is equal to S, and ES of X is equal to 0 if X not equal to S. So this map S is mapped to the uh, map ES, where ES takes 1 only at S, and at all other points it is 0. Okay. So observation is uh, any H belongs to F, or any H belongs to F, you have there exist some finitely many ES. There exist S1, S2, so on to say Sn belongs to S, such that H is the summation of uh, SIs times P of SIs at S belongs to this I's from 1 to N. Because see, H will take non-zero value at only finitely many uh, points. So these SIs are nothing but the points where it takes finitely many values. So you can write this H as this sum. Okay, so this is again you can say the most obvious thing to do. So then clearly, maybe I would say check that this F with the map gamma is a free Z module on S. Okay. So now, yes, we are in position to define what is a tensor product, and I will say define the construction of it. The next thing is,
Sir,
yes, Vivek.
sir, S tends to F and again S tends to arrow, that is arrow E5.
It's not tens. It's a map from S to F. And this is small f S that is an element of S that is mapped to ES, which is an element of F. Do you understand what's happening? So gamma is a map from S to F, mapping this small element S to the map ES in F. ES is actually the image of S under gamma.
ES.
Huh. And ES is a map which is 1 only at S and 0 everywhere else. Okay.
Okay.
So now with this data, we are in position to construct tensor products. So what we require for that, M and N are two uh, Z modules. T of gamma, I'm using gamma, go to the same notation. T of gamma is a Z bilinear map, okay, and T is a Z module. So now we will construct the, and we have a map from a uh, Z bilinear map M cross N to T. That is your gamma. Okay. So how you can construct a tensor product on M and N? So step one is take S to be the set M cross N. Okay, so this is as a set. Collect all the pair, all the tuples from S and N. Then it is a set, so you can define a free module, free Z module, or a free abelian group on S in the way we did above. So it's a free Z module on S, and gamma, sorry, here it's gamma will come. So maybe I will use here alpha because gamma is coming for the free module thing. Na? So here say it's alpha, and gamma is the map that is coming with the free Z module. Free Z module has a map from S to F, right? So yes. Okay. So here F is what? F is the summation of any element of F can be written as in this way: H of Si, E of Si, right? So H of Si's are elements of S and E of Si are maps. So in the similar way, you can write. So here the set is M cross N. You need to define free module over M cross N. So the element will be from M cross N. So you have constant C depending on Mn, and the map E in place of ES we have EMN. So EMN is something that vanishes over everything except the M and N, and these are finite sums. We have to take finite sums of all possible kind, and this collection will be the free module over the set M cross N. So here CMN are from Z, and only finitely many of uh, only finitely many of coefficients are non-zero. Okay, so except finitely many things, this CMN should be zero. Okay, so yeah, this is a definition of a free module over M cross N. So, and gamma will be the map from S to F, sending the tuple M comma N to E of Mn. Same way. So here small s was mapped to Es. Here Mn is the element of S. It will be mapped to En. Okay. Now step two is to uh, consider the following elements of F. Following elements of F. So U is by R to be E M1 plus M2 comma N. So E is depending on M and N, choice of M and N. So E M1 plus M2 minus E Mn minus E, sorry, here it should be M2N, M1N, E M2, M2 comma N, and here M1, M2, and M belongs to M, and your N belongs to N. So this is one thing. You union it with the elements of the form E M N1 plus N2 minus E M N1 minus E M N2. So here M is inside M, and N1 and N2 are inside N. So you collect all these elements of all these kinds, then let H be the uh, subgroup of F generated by this R. Okay. Then step 3 is just to quotient. So from M cross N to F, you have the map gamma coming out of the free module, and then from F to F divided by F modulo H, you have the projection map phi, and this F quotient H is our T, the tensor product, and it comes with a bilinear map. So what is a bilinear map? From here to here, if you compose these two, alpha is nothing but phi composed of gamma, and this is bilinear that you can check. Why it is bilinear? That's why the nature of F is like H is like that. So here we are ensuring the bilinearity. So we are collecting the elements of this kind EM1 plus M2 comma N, EM1N and EM2N. So this, and we are quotienting it, the group generated by this. That means in FH, F quotient H, all these kind of elements will be zero, and all these kind of elements is zero. So that is ensuring the bilinearity. Okay. That's why H is defined in such a way so that we get a bilinearity. In F, because F was just a free module generated over M cross N, so it won't have a bilinearity. But to ensure bilinearity, we quotient it with H, and then whatever we got, it's actually the tensor product. Okay, so one can check that T and alpha is the tensor product of, I'm writing is the because tensor product if exists it's unique. Okay. Okay. So now let's go with the notations. So T is written as M tensor N, as the underlying ring is Z, so we will write Z here, and this alpha is a map from M cross N to T. We will denote the image of alpha M alpha Mn as, so from alpha to F you have gamma map which was sending M comma N to E of Mn. Okay, so it was E Mn, and then you are quotienting it, so it will be E Mn bar, and we will use the notation for it M tensor N. Okay. 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 So this is now examples, or maybe you can take it as exercises. These have already been discussed in the class. I'm not going to solve this again because that will take some time. I will just write the uh, facts because we are going to use these things in the solving the assignment. So first is, if you tensor any module with the zero module, then you will get the zero module. Okay. Second is, if you tensor a mod Z module with Z itself, then that will be isomorphic to the module itself. Third is Z modulo AZ. So this is in common practice we say ZA, the set of the group of all integers modulo A. So Z modulo AZ tensor with Z modulo BZ is isomorphic to Z modulo GCD of AN B times Z. Okay. So with the same spirit, one can define uh, tensor module, tensor product of R modules that I am not going to discuss, but one can do the similar kind of uh, map, define similar kind of maps. There the uh, bilinear being map is being replaced by the balanced map, and it satisfies the same kind of universal property. So it just you have to read it, and you will get everything is in the same spirit. Okay, so I think if you are now okay with the uh, revision part, then we may start the solving the uh, assignment. Okay, so let me just copy paste first question. If you have any doubt or any comment on the uh, theory part, then you can just let me know. We can rediscuss anything if you wish to. Otherwise, we will solve the problems. Yes. So the first problem is choose all the correct answers. So as I said already, we have discussed in the lectures that Z modulo and AZ, that is uh, Z say N tensor with Z So this just to use this thing. So this is just ZA tensor with ZB is equal to Z of GCD AB. Okay, so Zn tensor Zm. I'm just writing it in this notation is isomorphic to Z GCD of A and B. So here, let's say this is A, this is B, this is C, this is D, right? So simply you can see what is the GCD of 5 comma 7 is equal to 1, right? And uh, Z1 is what? This is nothing but 0. So there is only a single element in Z1, that is 0. So this option is correct. And here GCD of, simply just need to take the GCD and see 8662. So you have 2 here. That option is also correct. Here, since this is correct, this has to be cancelled. We have already seen it first, and this is also being cancelled. So here, A and B are correct, and C and D are not correct. Okay. Is there any doubt in that? No. Okay. Then we maybe we can move to the next question. It says let n belongs to n, then one has to choose all correct options. First is Zn tensor with Q is isomorphic to Q. Zn tensor with Q is equal to 0. Zn tensor with Q modulo Z is equal to 0. And Zn tensor with Z is equal to Zn tensor with Q modulo Z is Z, Zn. So, yeah. So, before going to that, I will just try to explain you one more thing. While defining the tensor product, we said that something is Z bilinear if f m1 plus m2 comma n is f m1. So here we are considering Z bilinearity. So this will implies f of uh, any alpha times m is, whether I will dot n is same as alpha times m comma uh, alpha times n. In general, for notation purpose, I will say m alpha comma n is this, because you can take m alpha is what here, m1 plus m2 and many times, uh, and uh, then you take m to be n many times, it will give you f mn. uh, f. So this will be f m plus m comma n. This will be happening in alpha r many times, and as this is equal to f mn plus f mn, this is f m comma n plus f comma n alpha many times. Then you fix this and take summation over n. So this will be f m n plus by the second property n r many times, and then this will be f of uh, m comma r n. Okay, so this is an easy check. And why I mentioned this, because we would be using it again and again. So this is a crucial thing. And The only difference we have while defining a Z module and a R module is uh, here this is already given by first two properties in Z module. Sorry, Z tensor product. But when you will be defining a Z balance, R balanced map, and then tensor product of R modules, then you have to consider this third property also. So this won't be given by the first two properties. But here, uh, in case of Z bilinearity and Z modules, the first two properties implied the third one. So, so you should uh, keep this in mind that whenever you are considering an R tensor product of R modules or an R balanced map, then this is always there. Okay, so we will use this thing again and again in almost every example. So, uh, yeah. So now we want to show that. First and second option are just you have to find Zn tensor with Q, and C and D can be handled at one time. Zn Q modulo Z, either it's 0 or Zn. So one of them will be correct and one of them will be incorrect. So let's first see uh, A and B together. That is, let's see what is Zn tensor Z. Okay. So it is nothing but the module generated by. So to come to the definition of tensor product once again. So it's a free module over M cross N under this map gamma. Gamma was mapping it to EMN, and with uh, this condition, the bar condition. So the LE element of F modulo H is of this form M tensor N, and it satisfies the properties of that we get after this quotienting. So this T is actually generated by this M tensor N elements, right? So I can write it as A tensor P such that instead of writing P, I will write it B. So yeah, such that A is inside Zn and B is inside Q. So let's take an arbitrary element, arbitrary generator. Okay. So we consider A tensor B. Okay. So then since your B is, maybe I don't need that. So you just consider A tensor B. Then this is equal to, I can multiply both sides of P with N, right? N is the same N, Zn. Okay. So this is same as, so this N I can take this side. Why? Due to this property that we saw, that if N is an integer, in particularly it's an element of the ring, then you have f of M alpha comma N is M comma alpha N. Okay, so we are having F to be a Z bilinear map, and the map to the tensor product is also Z bilinear. So you have this M tensor, uh, M alpha tensor N is M tensor alpha N. Okay, so this thing is there. I will just write there also while discussing it. Yeah, yeah. So this N I can take here. So this is A N tensor with E by N. Why is it so? Since uh, M alpha tensor N is equal to M tensor alpha N. So this order matters. Here alpha I am writing after m, and here alpha I am writing before n. Because in Z it is okay. But if you define an arbitrary R modules, then you choose m to be a right R module and n to be a left R module. So here the multiplication will happen from the right, and here the multiplication will happen from the left. So tensor product in general for R modules is defined by considering the first module to be a right module and second module to be the left module. Okay, so in Z left and right is same, because Z in Z you have the commutativity. Okay, so there it, it's okay, you can make sense, but in general it's not. Okay, so now what is this an? An is 0 inside Zn, right? It's a multiple of n. So anything that is a multiple of n will vanish inside Zn. So you get 0 tensor, tensor with something. And it's already discussed in the lecture notes that 0 tensor with anything will give you 0. So all its generators are 0 in this tensor product. So this implies this tensor product is itself 0, because all the generators are 0. This implies that that is isomorph. We are writing equal to 0. So our uh, one of the option is correct, and the second one is incorrect. So this one is okay, and this one is not. Now the second part we will see Zn tensor with Q modulo Z. And we want to see. So Zn tensor with Q modulo Z. So it's again been generated by elements of the form A. So uh, this we have to consider. So we know that Zn tensor Z with Q modulo Z is being generated by elements of the form A tensor B, such that A is inside Zn and B is inside Q modulo Z. Okay, with this is the generating set. Should try not write like that, because we are using it for modulo also. Now again let's consider an arbitrary generator of it. Let A tensor B, let's say consider A tensor B such that A is inside Zn and B is inside Q modulo Z. Then B is an element of Q by Z. That means B is of the form. Then there exists B dash belongs to Q such that B is B dash plus Z, because it's a quotient group of Q, right? So what is A tensor B then? A tensor B is nothing but you are tensoring A with an element of the form B prime plus Z, where B is a element of the Q, right? So you can write, so this Q is an rational number and A is a element of Zn. So again you do the same thing. You multiply both things, this B prime plus Z by n and divide it by n. So uh, then you can take this n here. So this will be what? This will be just B prime upon n plus Z. Just a minute. times n. This makes sense because b prime is a rational, b prime and by n is also rational, and so this belongs to q by z. So this makes sense, right? And this n you can take here to make it 0. This is a n tensor with b prime n plus z, and this an is 0 in zn. Thus, you have 0 tensor with something. So this is 0. An arbitrary generator is 0. That means the tensor product is generated by 0. And thus you have the tensor product Zn with Q is equal to 0. So simply the both the case, the tensor product is 0. Yeah. Any doubt on that? Not. Then let's move to the next part. So you have to choose the correct answers. Here also you have to solve two tensor products. First is Q tensor with Q over Z, and then Q Z modulo Z tensor with Q modulo Z over uh, Z. Something is missing here. Is I think some typo is here. Let me just check it. Huh? This doesn't make sense. This third option, it doesn't make sense, right? Let me just check what it is. How they miss this thing. Uh, it's Q modulo Z, it's only. So this is some typo. This is Q modulo Z. Okay. So we have to again solve two tensor products and then see which options are matching. So let us first consider this Q tensor with Q thing. So for A and B. So I'm not writing there the numbering, it's obvious, right? The first options are A and then B. So then let's do Q tensor Q thing. So here there are two options. First is 0 and second is q. So earlier what was happening that one of the tensor product was having a finite order elements and the second was having uh, the infinite order elements. So when you are taking the tensor product, you can actually take the coefficient from one from the right side to the left side, and then as the elements are of finite order in the left side module, so you could actually see that all generators were equal to 0. But here every element of q is of infinite order, uh, because it's we are considering it as a group under addition, except the identity, that is 0 itself. So you cannot do the same thing here. So we will try to see that whether it's 0 or not. So here the tensor product will actually be an infinite uh, group, uh, infinite module. So we have to use the universal property to actually say what is the tensor product. So just uh, see this. We have not seen such a question before. So we will define a map from Q cross Q to Q. So we are taking M and defining a map from M cross N. The obvious map, that is the multiplication map, it has to lie inside this Q. So that's why the domain is being picked to be Q. FPQ is just the multiplication map. That's the obvious thing we can do because we need it to be a bilinear map. So F is a bilinear map, right? So uh, uh, we have, so what's the situation now? You have Q cross Q to Q, a map F that is bilinear, and from Q cross to Q, this Q tensor Q, there always exists a map alpha that is also bilinear. So by the universal property of tensor product, the universal property of tensor product, what that universal property says that for any P and for any bilinear map from M cross N to P, uh, it induces R linear map, that is F tilde. That was the universal property. Now let me just go back once and recall it for you. Yes. Yes. Okay. So this is the Z module thing. We want it for tensor product. Yes. So for any so M cross N to the tensor product, there is a net bilinear map, and so and it has a universal property that from any M cross N to uh, any Z module with a bilinear map F, there exists a unique there exists a Z linear map from T to P such that this F compose alpha is equal to uh, F. Okay, so that's what we are using here. So because tensor product exists, we don't know whatever it is, but it exists, and this map is bilinear. So whatever the tensor product is, let's say it is Q tensor, we denote it with the same notation, Q tensor with Q over Z. So from here to here, there should be a linear map, okay, that is F delta such that F is F delta compose alpha, or yeah, first we have to take elements from uh, Q cross Q to Q tensor Q through alpha, and then we will apply F delta over it. Okay. So then what this says, this implies, so F is from, uh, so both these maps are from Q cross Q to Q. So F will take PQ, and this is gamma will take Q. But what is the alpha map? Alpha map was, it maps P comma 2 element to the tensor of P comma Q. That's the notation we use, right? It is E P comma Q then bar, right? And that we denoted by P tensor Q. Okay. So this will implies FPQ is same as F tilde P tensor. So that is one of the use of the tensor that it converts the bilinear problem over bilinear map to the problem over linear map. Here, the F is a bilinear map and F delta is a linear map. So it converts the bilinear problem into the linear problem. Okay. Now this is the map that we get by the universal property, and then our claim is, so it's a linear map. It's a uh, Z linear map. Z linear map means it's a Z homomorphism. So homomorphism, it is already there from Q tensor Q to Q. If we could show that the map this is coming from the universal property is actually injective and onto, then this map will be a isomorphism, and we will get that Q tensor Q over Z is isomorphic to Q itself. Okay, so claim is F delta is an isomorphism. Okay, so first is F delta is a Z module homomorphism, and this is by the definition of F delta itself. In the universal property itself, it is given that it's a Z linear. That is Z module homomorphism. Second thing we will check is onto. So why it is onto? So any element of Q, you can get a pre-image. So let say Q belongs to Q, then there exists one tensor Q such that F delta of one tensor Q. So any we pick any arbitrary element from this codomain, that is Q. Now we need to show that there exists something inside this domain such that that something is mapped to this element through this F mode, F delta. So we pick Q from small q from this Q, and we are saying that there exists one tensor Q such that F delta of one tensor Q, which is what? From here, this is F of 1 comma Q, and what was F of 1 comma Q by definition? This is just a multiplication, PQ. Okay, so here P is 1, so it will be just 1 dot Q, it is Q. So it's subjective, right? For all Q, there exists this pre-image such that it is mapped to Q. So onto is also there. Only thing we need to check now is injectivity. If we can show that it is injective, then it's in the tensor product of Q tensor Z over Q tensor with Q over Z is Q. So injectivity is the crucial part, and but the same trick we will be using again and again. So just notice it once, and then you will be familiar with that. So let something say R tensor. Oh, I cannot write as R tensor is. Say something X belongs to kernel of F delta. Okay, so we need to show that the kernel is 0. So let's say so X belongs to kernel of uh, this F delta, and F delta is from Q tensor with Q. So this is actually a subset of Q tensor with Q over Z. So Q tensor Q is generated by the elements of the form uh, PQ, right? So this is being generated by elements P tensor Q such that P belongs and Q. I should not write this notation for such that P and Q are both from Q, right? So X is inside this. That means then there exists Pi and Qi belongs to Q such that X can be written as a linear sum of these elements of this kind. So X is a linear sum of, say, I equal to 1 to K Pi tensor Qi, right? Now you can do one more thing. Yes. So these Pi's are rational numbers. Therefore, there exists Pi1 and Pi I2 belongs to Z such that Pi is nothing but Pi1 divided by Pi2, right? Because it's a rational number, so it's a ratio of just two integers. So you just write it like that. This implies X is summation of I equal to 1 to K Pi1 Pi2 answer with Q. Now we have the underlying ring to be Z, and this Pi1 is inside Z. So we can shift this Pi here in this way. So you just write it like that. This is 1 times Pi2 times Pi1 answer with Qi. Now this Pi1 can be shifted to this side. This is summation I equal to 1 K 1 upon Pi1 tensor over Pi1 to saying something. Okay. Now still this 1 upon Pi1 is there. We want to get rid of this also. So how we can do that? So again you do one trick. Take summation I equal to 1 to K 1 upon Pi1. That is okay. And then in this part you multiply the above thing and the you just multiply it with Pi1 and divide it by Pi1. Okay. And here it is Pi, oh sorry, here it is Pi2, right? I1 I took here and the denominator was Pi2. So you multiply and divide by Pi2. So it's Pi1 Qi, and then this is a integer, and underline uh, ring is also integer. So you can take this Pi1 to this side. This will give you summation I equal to 1 to K Pi2 by Pi2, and then this is Pi2 was shifted there. Here it remains Pi2 Pi1 and then Qi1. Now what is this? This is Pi, right? Pi1 divided by Pi2 is Pi, and this is Pi2 divided by Pi2 is 1, right? So what you get, your X is actually equal to, so X is actually equal to summation over I equal to 1 to K. Here it is 1 tensor Pi Qi. Here Qi1 I am writing, I should not write 1 here. It's just 12. Now this first coordinate is fixed, right? You are bearing just the second coordinate. So you can take the sum inside due to the linearity. This is 1 tensor with Pi Qi I equal to 1 to n. So this implies your x is this, right? This you can do for any arbitrary element. You need not to take even x is inside kernel. This we are doing for any arbitrary element. I haven't used anything from the kernel, right? This is something that is that will hold for any arbitrary element. If you want to say something, your speaker is on. Not then maybe I will. So yeah. Now since x belongs to kernel of f delta, right? Now we will use the portion that says x belongs to f kernel of f delta. But this calculation is what very important. Whatever we did, we are going to use it again and again. So just be familiar with this shifting of elements of the ring from one side to other side. That is very crucial while dealing with the tensor products. Now x belongs to kernel of f delta, means f delta x is equal to 0, which implies what was x? That was nothing but summation of I equal to 1 to k pi tensor qi. Now f delta is linear, right? So it's linear, so this summation will come outside and you are left with f delta pi. It should be tensor, not just cross. Sorry, this thing is due to z linearity of f delta. Now what is f delta pi? This is so, okay, so f delta x is equal to 0. That means that thing is equal to 0, right? So we have what is this? This is summation of I equal to 1 to k f tilde pi qi is nothing but f of pi qi, and that is nothing but just take the product of this, that is pi qi, and that is equal to 0, right? So here let's say this is question 1. So x now from 1, x is nothing but 1 tensor summation of pi qi, that is 0, and that is 1 tensor with 0 is 0. This implies kernel of f delta is nothing but 0 because x was an arbitrary element of the kernel, and thus f delta is injective. Onto and homomorphism was also there. This implies the tensor product of q with q over z is isomorphic to q. So the trick is you define a bilinear map, you will get a, due to the universal property, you will get a linear map, and you show that that linear map is actually onto and injective. Onto would be easier if you have defined it in a nice way, and injectivity, for injectivity you have to work out a bit. But you can guess the uh, tensor product, what it would be by just looking at the onto part. Onto part is very crucial because that will make you that will help you in guessing this. Okay, that you will realize in the uh, uh, next questions. Okay, so yeah, so it was q. So first option is correct and the second is wrong. And then we will see this qz tensor with qz is what. So here also we are taking the tensor product of two infinite modules, but the things won't go similarly to the above example, and I will tell you why. So this is again generated by an element of qz, tensor with an element of qz. So we will consider the generators only. So consider p by q plus z, tensor with z, tensor over z with r by s z. These are the an arbitrary generator of this thing, right? So this is inside qz tensor with qz, right? So now we will do this some manipulation here some thing we would arrange. So how we would do that? So this is same as P by Q. You multiply it by S upon S, Z, tensor Z. We can only move the elements of the ring. That is here underlining is Z. You cannot do like, okay, what I if I take the entire PQ here. No, you can move only the elements of the Z here because underlining is Z. Now that is same as uh, you keep this as here and you can uh, move this as to this side. Okay, so this is same as P upon QS plus Z tensor with Z and S R S plus Z. This S to S will cancel out. You are left with P Q S plus Z tensor over Z with R plus Z. Now R is a integer, right? So this is actually the quotient and that is Z and which is 0 of Q by Z, right? The 0 of Q by Z is this Z only, right? So this is same as P QS plus, I will denote it by maybe 0 bar tensor Z with 0 bar, the 0 element of this module, and anything that tensor with 0 will give you 0. So although we are taking the tensor product of two infinite modules, here we get 0 because one of the module is having elements of the finite order. All elements are of finite order in Q by Z, even if it's a infinite order group. So that's the property that we are using. And that's also not true always. That if you take the product of two Z modules, which are of uh, finite order, or in which every element is of finite order, then you would get 0. No, because we have already seen in the first example that Zm cross Zn is Z GCD of AB. So here Z8 tensor with Z6 was Z2, not 0. So this will also not be true always, that if you take the tensor product such that one of the module is having all elements of finite order, then the tensor product is 0. No. Okay. So then either you have to work with the generators, or you have to make the use of universal property by defining a nice bilinear map. Okay. You can see here that here the one module is of infinite order, and every element of Q is having infinite order, but this Zn is making it 0. But if you replace Q by Zm, you may not get 0 if N and M is having a non-trivial GCD. So you cannot like make a uniform statement. You have to work with examples. So that's the idea. I think if it is okay, then we can move to the next question. Yeah. So it says again, choose all correct options. And here we just need to check one module, one tensor product. All the four options are having the single tensor product, that is R tensor Q. We need to check whether it's Q, R, 0, and Z. Okay. So, yeah. So the solution is So here both the modules are having elements of infinite order. R is having an elements of infinite orders, and Q is also having elements of infinite order. So there, that trick of making the mode tensor product zero will not work. So it expected that this should not be equal to zero. Okay. So one thing you can cancel out by that, but the other things are needed to be checked. Okay, this zero part you can remove, and for if it is not zero, then I told you a simple trick, right? You just try to define a bilinear map. So define f from uh, r cross q, the set to r, such that what's the obvious thing that we did last time? This is just fpq is pq, right? So from here itself, you can get an idea that why this option is also not correct and this is also not correct. Because this FQ has to lie inside R, right? You are taking element from R and multiplying it with an element of Q. The element has to lie inside R. You cannot restrict it to Q or Z. Of course, we need to show that it's a surjective and injective map. Sorry, it will induce a surjective and injective map, but by intuition only you can discard other two options, because the obvious bilinear map is to just multiply the elements, and that is will have the codomain to be R, and then this codomain is actually the suspect of the tensor product, right? So yeah, but we will definitely see this formally. So then this map is bilinear, and hence you have, so if you have anything from m cross n to some module p, bilinear map, then by the universal property of tensor product, the universal property of tensor products, uh, there exists linear map f delta from a tensor r tensor. So they are all z modules we are considering. So here it will come z to r, such that f delta composed with p tensor q is PQ. Similarly, the way we did in the last example, because the map is also the same. So f delta p tensor q is actually f of pq, and that is nothing but pq. You can also see this by the map. So you have from r cross k, r cross q to r, the map f, which is a bilinear map. You already have a map from r cross q to r tensor q. It maps every pair to uh, every p comma q tuple to the tensor p tensor q, and then uh, from here to here you induce this map f delta, which is linear, and that sends p tensor q to f of pq, which is just pq. Okay, so That's what the idea is. Then uh, this is linear. So first thing is done, linear thing is done, and we just need to check the onto part and the subject injective part. So onto part is again easy. Onto is just for all uh, re real numbers, say how to x belongs to R. There exists x tensor with z 1. So see, I am taking x tensor z, not one tensor x, because this part should be inside R and this part should be inside Q. Okay, so I cannot take one tensor x because x is a real number. So I cannot take x here because here the domain is Q. So x tensor 1 such that f delta of x tensor z 1 is just x dot 1, which is x. So it is surjective, and injectivity needs a little bit of work in the same way that we did last time. So let x equal to summation of some pi tensor with qi, I equal to 1 to k, uh, belongs to kernel of f delta, and kernel of f delta was inside R tensor with q. So these things are inside R and this is inside Q. So we will make use of this Qi in the same way that we did in the last example. So you write here, since Qi is since Qi belongs to Q, uh, therefore there exists Qi1 and Qi2 belongs to Z, such that each Qi is just the ratio of them, Qi1, Qi2, and then you proceed to the similarly to the last example. This is summation k I equal to 1 to k pi tensor uh, qi1 qi2. Okay, then you first shift here the qi1 part and then the qi2 part. So similar to the solution of the last problem. This is actually equal to summation of, now this time this one will be here, pi qi tensor with 1 I equal to 1 to k, and that will be uh, yeah, you can take summation inside. Here the summation is outside, so summation pi qi whole tensor with 1, because 1 is now fixed, right? So you can use the linearity. This implies x is equal to this, and now you use this thing that since x belongs to kernel of f delta, therefore f delta of x, that is f delta of summation I equal to 1 to k uh, pi tensor with qi, that is f is linear, so you can take it inside pi tensor qi, which is just summation of pi qi, and that is equal to 0 because it is inside x. This will implies x, which is the summation of pi qi tensor with 1 is nothing but 0 tensor with 1, which is 0, and thus f is injective, and you got R tensor with q over z is same as R. Okay. The same thing we are doing for injectivity, nothing uh, else. So this B option is correct. Although we have already discarded the other three options, but we need to see that actually whatever we are doing is correct. So yeah. So with that, I think we can move to the next question. Now I will try to wind up quickly because I have already defined a lot in the revision, and then we have seen a number of examples. So it's just to uh, see the idea rather than being more focused on the solution. So then it says, so question 5 says Z tensor with Z modulo 5Z and Z B is 5Z tensor with Z modulo 5Z. Choose all the correct answer. So we have to see whether 5 tensor 2 is 0 in A and is it 0 in B. So 5 so this is very easy to see actually. So in A, first of all, we will see, so 5 tensor 2 is, so A is Z tensor with Z modulo 5Z. So here we just need elements from the Z. So we can write it like 1.5 tensor with 2. This one can be moved here. This is 1 tensor with 5.2. So this is 1 tensor with 10, and that is 0 bar in Z modulo 5Z. So this is nothing but 1 tensor with 0 bar, and that is 0. So it is 0 in A, but let's see what happens in B. In B, it's the 5 tensor 2. Now here, the domain is 5Z. Okay. So uh, this is 5Z tensor Z modulo 5Z. Tensor Z modulo 5Z. Right. So here the element should be from, this should be inside 5Z only. Okay. So here 5 cannot be moved to the other side, since if 5 is moved, then what is left here? 1, and 1 is not inside the domain, the 5Z. So 1 is not inside 5Z, so we cannot move it to the other side, and this implies 5 tensor 2 is not equal to 0 in B. Okay. Okay. So uh, then I think we can move to the next question. Really, running out of time. So yeah, it says let S subset of R is a subring of ring R such that both have common identity element. Choose all the correct options. S is a, R is a right S module. So you can define the right module structure over S in the uh, just a common most usual way. So you define R dot S. So S is, you have to define the right S module. So element of F should be operating from the right. You just define it a multiplication as RS. Okay, so it's of course it lies inside R. So this will make it a right S module. You can check. Okay. Second is R tensor with S is a left R module. So here you, the multiplication is from right, sorry, left, and the element R of so R dash I will take R dash R tensor S. On R tensor S, it will operate. So this will be just to define R dash R. It will lie inside S, so there is no problem. It's an element of R tensor S again, and you check that it satisfies the properties of module. So this is the map. Then the question is R tensor S is isomorphic to R or R tensor S is isomorphic to S. So that needs a work to be done. So we define the map from the same kind of map we will define F from R cross S to F. I won't say the domain. So you guess it. It is from again the same kind of thing we will do. F R of S is just you multiply them both RS. So S is a subring, not an ideal. If it would have been ideal, then we would have kept it as here, but it's a subring, so RS may not lie inside this S. We have to take the entire ring R. Okay. So, and here the unity part will play a role, that it has the common identity element in showing the subjectivity. Okay. So then since then this map is a R balanced map. So balanced map can be defined in the same spirit as we define Z bilinear map with two properties of the linearity in two coordinates, and then the scalar multiplication thing that I said will be implied by the first two. So that is not directly implied in case of an arbitrary uh, ring, but over Z it was coming. So here the underlying ring is S. We are taking tensor product over S. So it won't directly follow. Okay, so for balanced map, we define that third property also. So I am skipping the definition of it. You just have a look at that. So by the universal property of tensor products, you will get a map. There exists a linear map that it is over S. So S linear map. Let's write it a bit clear. There exists a S linear map F F delta from R tensor S R so such that F tensor of F delta of R tensor S is F of R comma S, that is RS. Okay, and then similarly you check that F delta is an isomorphism. Linearity is there, onto is obvious. Again, you can take an element R from here, and then you can get the pre-images R tensor 1. One is the unity in S and one is the unity in R. That is R dot 1 will be R again in again. Okay. So that's why the common identity element was needed in showing the uh, onto part. So I'm leaving it to you in the same way that we have done the above examples, it will follow. Let me just quickly give hints of the next 2 3 questions, and then I will stop. 7th question is actually a tricky question. So I will give some steps solution, and then you have to uh, proceed accordingly. Solution is, so it says, let R be a commutative ring, I and J be ideals of R. Choose all the correct options. So we need to see, first of all, whether R tensor I, what is R tensor I? So ABC part will be handled in that way, and then we have to see this second thing. So since I is an ideal of R, then, so ideal means left and right both. Yes, but it's a commutative ring. So left and right, it will be both. Okay. In commutative ring, there is nothing like left on right, because left ideal is by default right ideal. It's a commutative ring. No? So I is an ideal of R, then I is a R module, and thus we have seen that R tensor R with I is going to be isomorphic to I again. Okay, we saw now that Z tensor with M over Z is isomorphic to M. So in the same way, you can see that for any ring R, it follows. Okay, then you have this to be wrong, this to be wrong, and this to be correct. And this is also correct, that you check using the property that I will tell you. It takes some time, and but you define the map in the usual sense. Map one element of a. So let me tell you what property you need for that. So R modulo I plus J is uh, isomorphic to R modulo J, and then you modulo I times R modulo J. So this is product of rings. So Rj is a ring, I is a ring. So you define I dot Rj by just the multiplication thing, and then Rj modulo I dot Rj. This is same as I modulo R plus J, and you define the map from R modulo I to R modulo J from here to this uh, this thing, and then you check the surjectivity and injectivity thing. It will follow. Okay. Yeah, I think then it's better to uh, quickly say few things about the next questions also, because we have already run out of time. Question number 8. Let me write down. So it says here we need to check two things. Zi tensor with R is isomorphic to R or Zi, and Zi tensor with uh, uh, C is isomorphic to C. So solution is to define uh, the similar kind of map here also, that is F from Zi cross R. Again, I won't say the uh, domain, codomain. First of all, we need to see the such that f of, so what an element of a plus zi, this is a plus bi, and an arbitrary element of R is, let's say, C. You just define the multiplication in the usual sense. That's CA plus ICB. Okay, CA plus ICB. So see, this is inside C. This is not inside R because this is uh, I'm saying C is an element of R, na. So it's a map from Zi to Zi cross R to something. So the domain codomain will be C. So it cannot be inside R. It cannot be inside Zi because here these are real numbers, not integers. So this should be correct. Okay. Then using it, it is a bilinear map. It is a bilinear map. So use the the universal property of tensor products to show that Zi tensor with Z R is isomorphic to C. Okay. So similarly, you can show that Zi tensor C is isomorphic to C. The same map will work. Here, instead of C, will there will be some alpha, and you define the multiplication in the complex numbers. So that will work. So D similarly Zi tensor with Z over C is isomorphic to C. Okay. So this is it. Session. I will just say if I can say something about the next two questions. Yeah, I can say. Just I will define the map and then you can handle. I hope. Okay. So true or false? QX tensor with QX is QX. So I will define the map for you, and then you check uh, it of your own. So the map is define f from qx cross qx2 qx such that f of axn bxm is ab x n plus m, and this is for single terms. You extend it uh, and extend it linearly. Okay, and then check that this is actually true. Qx by the same the universal property, again you will get that this is actually isomorphic to Qx. So this is true. Okay. The last question is uh, so we have handled these questions of so many times these things. So these are just checking. Only thing is you need to define a nice map, and that's I'm doing for you. So you just check the uh, universal property plays the nice role, and then it will be over. So it says now 10th question says R is a commutative ring and M and R are or R modules. Then M tensor R is same as N tensor M. So you define F from uh, M cross N to N tensor M such that F of M comma N is N tensor M. Okay. So uh, using universal property, this will induce this will induce a map F delta from M tensor N to N tensor M, and similarly to define G from N cross M to M tensor Rn. In the same way, you G of Nm, you just map it to such that G of Nm is M tensor N. Then again by using the universal property, you check the intermediate details, right? That it's a balanced map and uh, all. Universal property, this will induce a map. So this map is R balanced. So then check that it is a R balanced map. That I'm leaving to you, because for using the universal property, you need to check that it's a R balanced map. Okay. Similarly, here also you need to check that R balanced. Check that G is a R balanced map. So this will induce a map G delta from uh, N tensor M to M tensor R, and then it's obvious that uh, G delta uh, composed with F is same as F delta composed with G, and that is identity. Okay, so thus you have N tensor M is same as is isomorphic to M tensor. Okay, so yeah, so we have finished this assignment. In the next session, we will see assignment number uh, 10. If you have any doubt, then you can ask. Otherwise, I will stop here. Okay, any doubt? I will assume then let's do that. You're writing in the chat. No, sir. Okay, then. So I will stop here. We will meet on the next Tuesday uh, at the same time, and there will be one. And there will be one uh, uh, 1 hour session, so that you will be informed by the NPTEL team. Okay. Okay then. Bye. Good night.